This is your first video for production of materials, and it's on alkanes and alkenes. Now this, you'll remember, is linked into your prelim syllabus, so a lot of what we cover today you'll know and remember, but it's going to have a strong link into your first HSC practical, which is going to be the reactions of hydrocarbons with bromine water. Hopefully you'll recognise this list as being the alkanes. And alkanes are special in that they have a single bond. And let's say if we were to draw ethane here, so we have two carbons, see that single bond between them, and then there's a single bond to the hydrogens. So if we draw this out, you'll see that it has a pattern between all the alkanes, and that's its homologous series. So in this case, for alkanes, just to refresh your memory, it's CnH2n plus 2. So that's a general equation if you want to remember how to write all the alkanes. Now when it comes to naming alkanes is very simple. The first part of it has to relate to how many carbons there are. So in the case of the number 10, 10 means dec. So you've got your dec, and the ane at the end is signifying a single bond. So all the 10 carbons that are bonded together are bonded by single bonds. So it's called decane. Now on the other side of this, we have our alkenes. Now our alkenes are very similar to our alkanes in terms of naming. So meth means 1, eth means 2. And the ending is the same. However, we change it to the ene. And the ene is representing a double bond somewhere present in that structure. So what I'd like you to do now as part of a bit of revision is to pause the video and write out a list similar to what we have here on your alkanes. So write the general formula and the name given to the first, up to deca, of the first alkenes, and then continue on with the video. So I've written a couple out here, so check your answers. Hopefully you haven't fallen for the trap of coming up with a methane. Methane, seeing as there's only one carbon, you can't have a carbon double bonding to itself. So the first of the alkenes will be your ethene, which is C2H4. Then we've got our propene, butene, pentene, and hexene, all the way up to our decene. But you'll notice that, again, they have very similar naming conventions. And in this case, and I'll just change colour here so that it's noticeable, it's going to be CnH2n for our alkenes. So it's nice and simple there. So hopefully this is all nice and refreshed into your mind. So let's continue looking at the reactivity of our alkanes and alkenes. And to demonstrate it, I'm going to be using our halogens. And in particular, I'm going to use the example of chlorine. So just remember, chlorine is diatomic, and it's going to be in a gaseous state when we use it. And I'm going to use the halogens because they have a high electronegativity. So they love electrons. And this is going to be great in terms of showing the difference between our single bond and our double bond. So let's start with an alkane, and we're going to use methane for this example. So writing out methane, CH4, and it's going to be in a gaseous state because remember the smaller chains are going to have a lower boiling point. So these are going to be in a gas state. And then we're going to add some chlorine gas as well. Now what happens is, when we have our methane and we're adding our chlorine gas, it has to be under the presence of UV light. If there is no UV, let's say you're in a dark room or perhaps just don't have UV lights, the reaction won't take place. Well, it does take place, but it's extremely slow. So the UV makes this happen. And what specifically happens here is something called a substitution reaction. So I'll just write that here, Okay, so it's a substitution reaction. We're actually going to substitute one of these hydrogen atoms for one of these chlorines. So we're going to create CH3Cl. Now, what do we do with the leftovers? And again, this is in a gas state. And we're going to add that to the leftover hydrogen and create our hydrogen chloride gas. So as you can see, this is a substitution reaction. It has to happen under UV or nothing's going to happen at all. So let's have a look. What if I do the same thing, but instead I use ethene? So I'm using an alkene. So with our ethene, C2H4, and again that's going to be a gas as well, I'll add my chlorine gas. But in this case, something different is going to happen because of the double bond, something that's called an addition reaction. And UV doesn't need to be present for this to happen. So rather than actually substituting like we do in an alkene, one hydrogen for the chlorine, in this case the chlorine gas is going to be added to our ethene. So it bungs itself pretty much straight on the end in an equation. But what I want you to do, think about the double bond. Think about what's actually happening between the methane and it being substituted for a chlorine, and the difference between the ethene, where it's an addition reaction. Try to draw these two equations molecularly. So give that a go, pause the video, and then we'll have a look. So let's have a look if you were correct. Now let's start with methane, so our alkane. So in this case, when we look at our results, we have our standard methane here, but what's happened is this hydrogen has been substituted for a chlorine atom. And then of course, because this has been broken off and has been swapped around, same here, this chlorine, because it's moved over here, is going to be replaced with a hydrogen. So again, this is a substitution reaction. So let's have a look at our ethene. So here in our ethene, you can see our double bond between the carbons, and we have our chlorines. So this is an addition reaction. We're adding, or addition reaction. We are adding the chlorine to our ethene. And you can see what's happened here. The double bond between the carbon has broken, and chlorine has attached itself. Okay, so it's added itself to the molecule. And that's the process. That's what's going to make ethene or any alkene so reactive, because this double bond can be broken and any other molecule can be attached to it. So how is this going to relate to the practical that you're going to do in class? The practical is looking at the reactions of hydrocarbons with bromine water. Now remember that your hydrocarbons are your alkenes and alkanes, and you'll need to find a corresponding pair. So that means that you can't really compare methane to ethene because they're two different things. You could compare ethene to ethane, but the problem with that, you need to find something that's suitable. And when I say suitable, I mean for this experiment, let's imagine here that you've got a lovely conical flask here, and down the water we have some bromine water, and you add, let's say, your ethene, C2H4, that's in a gaseous state. So when you add it, you're going to have all your alkene up here, your bromine water down here, and there's no reaction going to take place. So go online, have a look, see what other hydrocarbons people are using and what might be suitable for this experiment. But just make sure that you have one alkane and one alkene, and that they're the corresponding pair, so that they have the same number of carbons. Same number of carbons. Okay, now let's focus a little more on what bromine water is. Bromine, you should know as one of your halogens, and it's going to undergo the same reaction as we saw with chlorine. So bromine again is diatomic, and it exists in this case in water. So we're going to make bromine water, which is going to add bromine to water, so bromine plus water. Now the important thing to remember, this does actually react. It is an equilibrium reaction though, so you'll notice the double-ended poorly drawn arrow. So what will happen is you will get different products. However, you need to remember this reaction is heavily focused to the left, which means that whilst you will have these products in your conical flask or in your test tube, there's not going to be a lot of them because this reaction prefers to sit like this with the diatomic bromine and water molecules on their own. So when it comes to writing this in the HSC or even in your prac write-up, it is completely acceptable just to have bromine in diatomic in an aqueous state, and that we know kind of links in with bromine water. You don't necessarily need to include these parts or these products of the reaction. So what I'd like you to do now, have a look at your prac book, fill out the missing pieces, do some research to find an appropriate hydrocarbon to use, and I'll see you in class.